Okay, we're looking at potential energy diagrams, and we're going to do the warm-up. It says complete the following table by placing a check mark in the appropriate energy change column for each chemical change classification listed. If we have a synthesis reaction, synthesis reactions tend to release heat, so this is exothermic. And then a decomposition reaction is the reverse of a synthesis reaction, so that means this would be endothermic. Neutralization reactions, they tend to release a little bit of heat, so they are exothermic. Combustion reactions definitely release heat, so they're also exothermic. And we're going to be talking about sources of energy. Things like natural gas, wood, coal, and gasoline provide us with energy. And most energy is stored as chemical potential energy in the form of bonds, and we can convert that into heat when we break the bonds. And the amount of potential energy that's available depends upon a couple of things. It depends upon the position of subatomic particles making up a sample, and it also depends upon the composition of the sample, meaning what is that sample made up of. And delta H is what we use to symbolize the change in energy that's available as heat. It is sometimes read as delta H or enthalpy change. So enthalpy is potential energy that can be given off or absorbed as heat. And if you take a look here, there are all sorts of processes, physical and chemical processes, like maybe if you're melting ice or you're decomposing water into hydrogen and oxygen, they have enthalpy changes associated with them. And you'll notice that here we have a combustion reaction, which releases heat energy, and off to the side they say the delta H of combustion for this reaction, since it's a combustion reaction, they refer to it as such. It equals negative 2221 kilojoules per mole. This negative is symbolic of the fact that it is releasing heat energy, and therefore this is exothermic, okay? What causes the enthalpy that's stored in reactants to be different from that that's stored in products? Well, it's going to be the chemical bonds. So the energy of chemical bonds is related to the electrons in atoms and molecules, and they have potential energy. And if we pull those electrons away from the positively charged nucleus of their atom, then what happens is there's that potential energy between the two, and we call that bond energy. So when we break bonds, we require energy. Think of it as if you're karate chopping a piece of wood, that would require an energy input. And if we're forming bonds, which is the opposite of breaking them, that means that energy would be released, since energy is required to break them. So breaking chemical bonds requires energy, and that energy is used to overcome the electrostatic force between that's binding the atoms or the ions together, and that electrostatic force between the protons and the electrons. And the bond formation is a more stable situation, and that's why energy is being released. So the more energy that's absorbed as bonds break than is released as bonds are forming during a chemical change, that means you'd have a net absorption of energy, and that would be an endothermic process, and that's when your delta H will be positive. So the energy absorbed to break bonds, when that is greater than the energy released, we have an overall endothermic reaction. Your delta H would be positive. If more energy is released during bond formation than it is absorbed during bond breaking, we have an exothermic reaction, and you're going to have a negative delta H value. Now, there are always two ways to represent the delta H values that are associated with a chemical reaction. One of them is known as a thermochemical equation. That's where we have the energy change as part of the chemical equation. And The delta H notation is when we have it written after it. So for instance, here in the quick check, we have a thermochemical equation with the delta H inside the equation. When it's on the product side, that means it is going to be an exothermic reaction. If you had this 92.2 kilojoules per mole on the reactant side of the equation, it would be endothermic. If it's in the equation, it is simply a positive value. Okay, it doesn't matter if it's exo or endo. You decipher whether it is endo or exo by where it is. Okay, delta H notation has your balanced chemical equation with the delta H specifically after it with its value. If it's endothermic, it's positive. If it's exothermic, it has this negative symbol in front of it. Okay, so here in the quick check, we are given some delta H values, and they want us to write a balanced thermochemical equation and an equation using delta H notation with the smallest possible whole number coefficients for each of the following chemical changes. Note that the units imply that the energy released or absorbed is for a mole of the reacting species. The first one is done for you. So here they said we're going to have the delta H synthesis of NH3, meaning we're synthesizing NH3, we are making it in a synthesis reaction. You have N2 combining with H2 to give you NH3, you balance it, and the reason that this is 92.2 rather than 46.1 is because you have a coefficient of 2 in front of the NH3, okay? Now, we're going to take a look at number 2. Number 2 says we're looking at the combustion of C2H6. So what you're going to do is you have your C2H6. Combustion means it's reacting with oxygen. You're producing carbon dioxide and water. If we were to balance this, we would end up with a 2 in front of C2H6, a 7 in front of O2, a 4 in front of CO2, and a 6 in front of H2O. Now, since the unit on the delta H is kilojoules per 1 mole of C2H6, and the coefficient in front of C2H6 is a 2, we have to multiply this 1428.5 by 2. So if I'm writing my thermochemical equation, here, that means that my delta H value has to be a part of the equation. So since this is a negative delta H, then this is an exothermic process, I would be writing this on the product side. So this would be plus 2 times 1428.5. This is 2857 kilojoules per mole. Okay? If I wanted the delta H notation, then I would write the exact same thing, but I wouldn't include the delta H value in the overall reaction. I would simply write that the delta H for this process is negative 2857 kilojoules per mole. This time it's negative because the delta H is outside of the equation. I need to represent whether it's exothermic or endothermic. Okay? For number 3, we're looking at the decomposition of Hbr. That means that you've got Hbr decomposing into hydrogen and bromine. Those are both diatomic. You're going to put a 2 in front of Hbr. And if I'm writing the thermochemical equation, remember we have to include the delta H value within the equation. So here my Hbr is 36.1 kilojoules per 1 mole of Hbr. The coefficient in front of Hbr is a 2. So you need to multiply 36.1 by 2, which will give you 72.2. Since this is a positive value, that means this is endothermic, so I'm going to go ahead and stick this in here, 72.2 kilojoules per mole on the reactant side. Now, if I want my delta H notation, I'm going to do 2Hbr produces H2 and Br2. My delta H is equal to 72.2 kilojoules per mole. This is positive because this is endothermic. And you can put a little plus in front of the 72.2. You will often see that, okay? Okay, next page. Let's talk about transition state theory. So reactant molecules come together in a collision, and they slow down as they approach each other because their electron clouds, which are negatively charged, repel each other because like charges repel. Now, at some point, they collide and fly apart, but if a reaction occurs, the particles that separate are going to be different than those that came together during the initial collision. So when collision geometry is favorable and the colliding particles have enough kinetic energy to equal, at least equal, the activation energy, they're going to interact to form something called an activated complex. The activated complex is a high energy, really unstable transition configuration of atoms. This is where we are breaking the bonds of the reactants and we are forming the bonds of the products. So here in this figure, you'll notice that I've got hydrogen and iodine. They come together and collide. This in the middle here is my activated complex where the bonds between the hydrogens are breaking. Those are these dashed lines. And the bonds between the HIs are forming. Those are the dashed lines here on the top and the bottom. So this is my activated complex, and then you end up with your product because that is only a very transition configuration, and it will form new lower energy, more stable products. So if you take a look at potential energy profiles down here, this is a potential energy diagram, and this is a graphical representation of the energy changes that take place during a chemical reaction. You'll notice that on this axis, I have the potential energy in kilojoules per mole. You should know that. Potential energy is on the y-axis. I have the path that the reaction follows on the x-axis. Sometimes this is called the reaction pathway. And this curve, you'll notice that the potential energy of the reactants is here. We often will write in whatever the reactants are right here on this line. And the potential energy of the reactants is whatever this value is on the y-axis. And then you rise to a high point on this curve. This is where your activated complex is. If you want to get the potential energy of it, you have to go over to the y-axis to get the potential energy of the activated complex. Wherever the reactants began, in terms of their potential energy here, to the highest point on the graph where the activated complex is, this difference here is known as the activation energy. You'll notice that my products are down here and they have less potential energy than the reactants do. So this curve, moving from left to right, is how the curve looks for an exothermic process. If I want to calculate the delta H, or the heat of reaction, or the enthalpy change, you have to take the potential energy of the products, which is from this point down here, minus the potential energy of the reactants. So this region here is where you would get the delta H. Now, if it's an exothermic process, your delta H will be negative when you subtract the potential energy of the products and the potential energy of the reactants, okay? If you take a look at the next page, here in this sample problem, you'll notice that this curve looks a little bit different, okay? Is this reaction endothermic or exothermic? Well, my reactants are here, and their potential energy is 20 kilojoules per mole. My products are here, and their potential energy is 40 kilojoules per mole. So that means that this difference here is going to be my delta H. So 40 minus 20 is going to give me 20 kilojoules per mole, and it's positive. And when your delta H is positive, it's an endothermic process. So this curve is how an endothermic process would look. The products have more potential energy than the reactants. Now, what if I wanted to get the activation energy? The activation energy is wherever the reactants begin, which is 20 kilojoules per mole, to the highest point on the graph. So this is going to end up being 100 minus 20, which would be 80 kilojoules per mole for the activation energy. So the potential energy of the reactants was 20, products was 40, activation energy was 100 minus 20, which is 80 kilojoules per mole. The highest point on the graph is where your activated complex is, and its potential energy is 100 kilojoules per mole. Okay? Now, sometimes reactions are reversible. Okay? So if we take a look at the next page, here, you'll notice that we have, on the left, this is an exothermic process in the forward direction, moving from left to right. Okay? If I were to move in the reverse direction, from right to left, that would be an endothermic curve, because my products are ending up at a higher point. Now, they simply took this and they reversed it to show you what the reverse reaction would look like. Okay? But potential energy diagrams can often be read in reverse order. So if you take a look here at this sample problem, the forward reaction going from left to right is exothermic. The reverse reaction is endothermic. The delta H of the forward reaction is going to be between here and here. So you're going to end up having the product potential energy 10 minus the reactant potential energy 20, and you get negative 10 kilojoules per mole. If I were to calculate the delta H for the reverse reaction, then I would take 20 minus 10, and I'd get a positive 10, because that's an endothermic process. The activation energy for the forward reaction is wherever the reactants are to the highest point. So this is 50 minus 20, which is 30 kilojoules per mole. But if I want the activation energy for the reverse reaction, that means that this is my reactant here, and this is the highest point on the graph. So this is going to be 50 minus 10, which is 40 kilojoules per mole. Okay? The potential energy for the activated complex, my activated complex is up here at the top. 50 is going to be the kilojoules per mole for that, and it is the same for the forward and the reverse reaction. Now let's take a look at the practice problems here. Is the forward reaction exo or endo? Well, this is going to be endo, because my potential energy of my product is higher than the potential energy of the reactant. And what is the activation energy for the forward direction? Well, between here and here, this is 140 minus 110. So this is going to be 30 kilojoules per mole. What's the enthalpy change? Well, that's wherever the products and the reactants are. So this is 130 minus 110. So you're going to end up with a positive 20 kilojoules per mole. And then what's the potential energy of the products? Well, it's 130 kilojoules per mole. And the potential energy of the activated complex here is 140 kilojoules per mole. Number 2. Indicate the meaning of each of the measured values, 1 through 4, on the following potential energy diagram. Okay, so this right here is the forward reaction. So between where the reactants are and the highest point of the graph, 1 is going to be the activation energy of the forward reaction. Okay. For number 2 here, these are the reactants. Okay. So number 2 is going to be the potential energy of the reactants. Okay. Number 3 is between the product here and the highest point on the graph, which means this is going to be the reverse reaction's activation energy. And then item number 4, this is going to be the delta H of the reaction, the enthalpy change. Let's talk about a summary for reversible diagrams down here. The delta H of the forward and reverse reactions is always going to be the same magnitude, but it's going to have opposite signs. The activation energy is always smaller for exothermic reactions. And if we change the temperature, the pressure, the concentration, or the surface area, there is no effect on the potential energy diagram. Next page. Let's talk about activation energy and catalysis. When you increase the temperature or concentration, there are going to be more collisions. And in general, catalysts are going to provide an alternate pathway where we have a lower energy activated complex that can form. And when we have an alternate pathway, these are called mechanisms. We briefly mentioned this in another section. And catalysts provide additional pathways or an additional reaction mechanism, because reaction mechanisms are different steps in a reaction, okay? And that different step is going to have a lower activation energy, and that's why we end up with an increased reaction rate. You know that catalysts are not consumed or changed in a reaction. You may see you may see the catalyst consumed in a certain step, but it will inevitably be produced in a different step of your reaction mechanism, which is why the catalyst is not overall consumed or changed during a reaction, okay? So catalysts reduce activation energy for the same extent in a forward and reverse reaction. So that means that the forward and reverse reaction rates will increase by the same amount, okay? Here we're looking at a potential energy profile for a catalyzed reaction. So we have our, we have the presence of a catalyst here in this dashed line that has these multiple little peaks here. You will often see a multiple peak diagram when you have a catalyst present, okay? So potential energy profiles for catalyzed reactions usually involve the formation of one or more than one activated complex, so that's why you see more than one peak. So you'll notice that my activation energy came down for that dashed line that has the catalyst present, okay? Now let's take a look over here at this last quick check. Study the following potential energy diagrams for two independent reactions. For diagram 1, indicate what each of the measurements shown by the lettered arrows represents. For diagram 2, indicate the number that represents the same measurement in diagram 1. So they have completed A for us. So in A, oops, I just messed that up. I meant to hit this. Okay. So in A, this is the reverse uncatalyzed activation energy. And that's the same as number 2 in diagram 2. So if I'm looking at B here, B is the forward catalyzed activation energy, and that is the same as item number 3 in diagram 2. For C here, this is the decrease in the activation energy due to catalysis, and that is the same as item number 4 in diagram number 2. D here is the delta H, which is the same as item number 7 in diagram 2. E here is the forward uncatalyzed activation energy, which is the same as item number 6 in diagram 2. F here is the reversed catalyzed activation energy, which is the same as item number 1.